So the proof starts with the three, a preparatory lemma, 4.12.3, and not a very tough lemma, but what you have to notice about the notations. Slightly the notations are different in this particular proof, but this notation is not used everywhere. B naught is called a ball of radius 1 around 0, and Bn is the ball of radius 2 raised to minus n. Radius is 2 raised to minus n around 0 in x. That is the notation of this. So what it says is that what it says is, if t is a bounded linear operator from x onto y, it's a onto, then the image of TB naught, that is, the TB naught is the image under T, the map that is going to be in Y. This will contain an open ball around 0 in Y. So what it says is that T0 will go to 0, therefore 0 is in Y. So T0 will be mapped to T0. So if you take a ball around the 0 in the space X, then there is a small ball around 0 in the image, namely TB naught. And the proof is not very difficult. That this I have already done it for you. Okay. So this if you fix any x, then there is a, you should understand what is KB1. It is a dilation of the ball of radius 1. What is KB1? Can you tell me?
Sir, unit KB1, sir, a ball with radius is 1/2 and center is 0.
No, that is different. KB1, K times B1. I am not talking about B of 0K. KB1, you look at the definition 1 on the top. We are multiplying every vector of B1 by K. So what will be the length
Yes,
of the vector now?
yes,
It will be
sir.
K, right?
Yes, okay, target.
So if the norm is less than or equal to 1, then the norm will be less than or equal to K. So what is KB1? It's a ball of radius K around 0. Clear?
Yes, sir. Yes, sir.
It is not radius with 2 raised to minus K. The notation is slightly different. That's why I'm saying be careful with this. The notation here is Bn. It is not n times b. Is it clear? N is the suffix here, not the multiplication. Here we are multiplying b1 by k. That's a dilation. This is called a dilation. If you have a ball of radius 1, if you multiply by 2, it becomes a ball of radius 2. That is, you are dilating the ball of radius 1 to ball of radius 2. Clear? Obviously, every element in so you can take k greater than 2. Okay, I mean, if you take x, any x, naturally it is going to be in one of the balls. This point is clear or not?
Yes, sir.
And therefore, if you look at Tx, that is the image of x under T, that is y. This is y because it is onto. So since T is surjective, the range will be the whole of y. And you have Tx, this is nothing but the set theory. Tx equal to T of union, and that is nothing but union of KTB1. And that is equal to k equal to 1 to infinity k. One way inclusion is simple. Second way inclusion is, if you take an element x in KTB1 closure, then it will be x will be in k plus 1 TB1 closure. Therefore, it will be instead of k, it will be k. So when you take the union, these two union remain the same. Clear? So by taking the closure, we do not further add points to the union. Please note, we do not add points to the union. Since y is complete, it is going to be a thick set in itself. So by case category theorem, hence noting that 3 is similar to 1, or when we conclude that KTB1, this k times TB1 for some k, contains an open, must contain an open bulk. If no k contains, that means every set will be non-dense. So that is not possible. So it has to be thick. If it is thick means it meager or thick, they are same. Non-meager is thick, okay? Meager is thin. Non-meager means there is a ball inside this one of this one. So it has to be in one of the balls. Call that as KTB1. So this implies that TB1 also contains a unit ball. So how do you get that one? TB1 closure. Whatever this KTB1 that ball has, you divide by the K, then it will come to, so you translate it back to 0. So that is what so it follows that B star, so that's the ball. I mean, I don't know what is the radius, so you call it as epsilon. Okay, so it's a ball of radius, why not? The only thing that you have to note is that this ball may not have the center at 0. It may have center somewhere else. So call that center as y naught. So if the ball is there, call B star equal to B star y. This is in TB1. Now you translate this by y naught, B star by y naught. That is B star minus y naught. Is same thing as the ball of radius 0 epsilon. That is contained in TB1 closure minus y naught. So that's a simple geometry. All right. Okay. That's the first thing. So that's what we wanted to show, right? You remember, no? What is that we want to show? Don't forget that, huh? We wanted to show here. Look at the A, part A. The closure of the image of the unit ball contains a ball of B star. That is the first thing that we have proved. Okay. All right. So now we prove the B part. B part is not difficult anyway. So we show that B star minus y naught is contained in T B naught closure. That's the thing that we proved by A, where B naught is given in the theorem. This we do by showing TB1 closure minus y naught is TB naught closure. Actually, we show contained. It's not a very difficult proof. Okay. So how do you show that? This I hope you understand B1. B1 is a ball of radius 0 with radius half. Okay, 2 raised to minus 1. So now let y belong to TB1 minus y naught. That is y plus y naught belongs to TB1 closure. We remember that y naught is in TB1 closure 2. So there are elements. What do you mean by it is in a closure? It could be a point in that one, or there is a sequence going. So you have a sequence UN equal to TW1. Why? Because the sequence is from TB1 closure. So this TWN is in TB1. Okay. That's what the point is. TW1, so there's a sequence in TW1, call that as TW1, call it as UN. That will converge to y plus y naught because it is in the closure. If you have a point in the closure, then there is a sequence from the set which will converge. That's what is used. Similarly, Vn equal to Tzn, which is in TB1, such that Vn goes to y naught. This is also true. Since Wn equal to Zn B1 and B1 has a radius of half, it follows that by the whatever the triangular inequality that the Wn minus the Zn is less than or equal to 1. So what it means is that the norm of Wn minus Zn is less than or equal to 1 says that it is in a ball of radius 1 around 0. Therefore, T of Wn minus Zn, that is same thing as T of Wn minus Tzn. This is because of linearity. This is un minus vn. Okay, this is un minus vn. Un converges to y plus y naught. Vn converges to y naught. Therefore, this un minus vn will converge to y. That's an obvious thing. Okay, I mean, you subtract these two, this y naught will cancel and you get a y here. Right? You can give a proof. So we see that since so y is in TB, so we see that y is, so this y now we have, it's nothing but the image of T of Wn Bn. Since it's an image of T of Wn and the Wn minus Z1 is less than or equal to 1, naturally y is in the image of TB1 closure. Y belong to TB1 minus y0 was arbitrary. This proves 5. What is this 5? Okay, let me see what is 5. This is the 5. This is what we wanted to show. Okay. So, I mean, the problem is now it's a question of using induction and you proceed with it. Okay. So from 4 we have b star minus y naught is b epsilon 0, b0 epsilon, that is nothing but TB naught closure that contained in that. This is the consequence of the Bayes theorem. Let Bn be equal to 0, the ball of radius 0, 2 raised to minus 1 as a radius. Then T is linear. So T of Bn closure will be 2 raised to minus 1 TB naught. Call Bn equal to B of ball of radius 0, epsilon by 2n. Instead of 1 by 2n, you call it as epsilon by 2n. Okay. Bn is radius epsilon 2 raised to minus n. Vn is it's epsilon by 2 raised to n. Now, why do you take this one? That will make this Vn contained in Tbn. Okay. Tbn is nothing but 2 raised to minus 1 into Tb naught. So this ball will be in Tbn actually. So finally we prove that this is a simple proof. Okay. I will leave that to you to prove it. Now we come to the main part of the theorem here. We prove that every open set A contained in A, the TA is open in Y. That is the, what is the theorem? The main theorem. This is the open mapping theorem. The T maps every open set to open set if T is onto. This is the main theorem. So we are going on to the proof of the main theorem. All right. Okay. Let me see where I am. Just 1 minute. And this we have done. This also we have done. Just 1 minute. Yeah, this is the, this part I am leaving it to as a reading assignment. You can read it yourself. Now we come to the proof. Proof of the main theorem becomes very simple. The moment you have uh, the two preparatory lemmas. Now, I would like to tell you something here. Many people don't use these two lemmas. Uh, I'm referring to the I'm referring to this part. This lemma 4.12.3. They don't prove A and B first, ABC first. What they do is they straight away put this part of the uh, proof of this theorem, this ABC, into part of that. But what happens is sometimes you don't, people don't ask questions. If you are attending an interview or something, they may not ask you to prove the open mapping theorem, but they may ask you one of these ABC. And therefore, it is better, these three parts of 4.12.3 ABC, they are independent of the theorem itself, although we use it. So these three questions can be asked separately in the exam, nothing to do with the open mapping theorem. All right. That is why I just wanted to give you this part here. Okay. Now now we prove that for every open set A contained in X, the TA is an open set in Y. That is, we want to show the map T is a open map given that T is an onto map. What does it mean? You take any open set A in X and we want to show TA is open. That's the thing that we have to show. This we do uh, for every Y in Tx belonging to TA. When you take T of A, whatever the given open set, so an element of TA will be looking like Tx, call that as Y, where this X is actually in A. Okay. So Y equal to Tx belongs to TA. Since A is open, please note X is in A. Okay. Since A is open and X is in A, so A minus X contains an open ball with radius 0. Let the radius of this open ball be R. Now set K equal to 1 by R or R equal to 1 by K. Then this K into A minus X, that is dilation of A minus X by K, contains a unit open ball by B0 by lemma whatever we have proved. Now this implies that K times A minus X will be actually K times TA minus Tx. That's obvious. Okay. This K times this K will be Ka, K into X will be Kx, and now we are operating this uh, T. So this will be K times TA minus Tx. That contains the open. So this K you can take it out. Okay. Dilation. What I mean is, 1 minute. K times T of K of A minus X. You have T of K times A minus X. Okay. This is same thing as K of T of A minus X. Why? Because if you look at this K times A minus X, what is this? This is nothing but the set of all Y such that, so Y equal to such that it is Y equal to K times A minus X. That means K times Z minus X, and Z is in K. That is in A. This is the definition. Okay. So when you take this T of, so you want to show that these two are same, right? So take say T in T times k of a minus x, you show that this implies that p is in k times t of a minus x. How do you show two sets are equal? A set E equal to G.
If all elements are equal, so
Yeah, if and only if E is contained in G and G is contained in E. This you have to show. So we have to show this and we have to show this, that P in K times T of A minus X, okay, is implies that this P is in T of K minus X. This is what you have to show. But if you use this definition, okay, so P is in K T minus X means what? T will be equal to this, use this definition. P, so I'm referring to this definition. P will be equal to what? It will be K of some Q minus X. Okay. So when you look at uh, so, so this is what you have, K into K into, so Ka minus X is this. You have to take T on that. Okay. So T of P will be T of KQ minus X. But T is linear. Okay. T is linear. So this will be K times T of Q minus X. TQ minus TX, right? Sorry. This will be K times TQ minus TX. So use this definition again. That will belong to that. So the simple set theory here, and that gives you this part. Okay? So that simple set theory gives you this. Now let the radius of the ball be R. What do you mean by radius of the ball be R? Yeah? So again, what you are using here is the fact that you take X in A. Okay? A is open, it's given. What are we trying to show? To show that T of A is open. This is the open mapping theorem. Okay. Now X is in A is open. This tells you that there is a ball of radius epsilon around X contained in A. Okay. Since it's open, that is what is used here. That's what is used here. So the A is open. It contains an open ball with of radius say R, and you, so essentially he says radius R. Okay, open ball. So I am using epsilon here. He is using R. Nothing more. Okay. So now you look at R equal to 1 by K, then K of A minus X will be T of K minus X that contains an open ball around 0. Therefore, Ta minus Tx, that is nothing but, so does Ta minus Tx because of the previous argument. Therefore, Ta contains an open ball around Tx equal to Y. Since Y is arbitrary, therefore, the set Ta is open. What do you mean by Ta is open? You take any point in Y, you have to show that there is an open ball. So take any point Y, that is Y. So call that as Y equal to Tx, X in A. That is because this Y is in the T. What do you mean by Y in TA? I mean, more of set theory, okay? Y in TA, image of A, implies that there exists X such that X is in A and Tx is Y. That is the definition of saying that it is in, this is the definition actually. So that finishes the proof of what is called the open mapping theorem. Okay. Finally, what it says is, since so arbitrary Ti is open. Finally, T inverse, if it exists, then by theorem, the T inverse is also linear and continuous. Essentially, what we are saying is, this part I will explain to you. It's not written properly. One, suppose T is a map from X to Y. T is, okay, 1, 1, or 2. If you want, you can say T inverse exists. T linear, this I have told you earlier, very first class. T inverse is linear from Y to X. Okay. T open map implies T inverse is continuous. This I have also told you. Why? If you have a map from a metric space, say M to N metric space, F is continuous if and only if F inverse is open set. E is open. Okay. If E open is open. That is, inverse image of open set is open. Inverse image of open set is open. Okay. Now, what is that? Instead of F, we have T inverse. Okay. So T inverse is from Y to X. So I want to, inverse image means what? You take the, so let U be X, U contained in X be open. To show that T inverse of U is F. Now when you look at T inverse of U, what will be T inverse of U? Sorry, there is something wrong. You take U, T inverse of open set is okay. So you have here U contained in X is open. Okay. But we want to show that T inverse of U is open. That is because of the previous part that what we have shown. So this T is continuous implies that T inverse of U, T inverse of the image of T inverse of the image of TU, that is nothing but U, is open. So that shows that if T is an open map, then the T inverse is a continuous map. That is the part of what we have done in metric spaces. Okay. If you want, I'll send a separate proof for you. All right.
Yes,
So,
sir.
or we can discuss it on. So that gives you the. Okay. So that tells you that if T is a onto map, T inverse is open. Since T inverse is open, the map T inverse is continuous. That is, T inverse is continuous means what? T inverse is bounded. T inverse is linear. Therefore, you can talk of what I wanted to tell you is this. Okay, let me give you this. Yeah, this is the open mapping theorem, bounded inverse theorem. Bounded inverse theorem means what? The inverse, if the inverse exists, it has to be a bounded map, right? What is the meaning of saying that it's a bounded map? It's a continuous map.
Yes,
Continuous
sir.
operator
Continue.
is same thing as a bounded linear operator. So we want to show the inverse is a continuous map, then it's a bounded map. That is why this theorem is also called bounded inverse theorem. Okay. So that is one story which I wanted to tell you today. The second story is about just give you an introduction and then do it for you. Okay. The next theorem is what is called closed top theorem. I will do it tomorrow. Okay. What it means is the following. So you have a map T from X to Y. This set G defined to be this, I think I have done it here. T comma X, X comma Tx contained in X cross Y. This set is called the graph of T. Please note it is contained in X cross Y. Okay. First thing, T is, say, T belongs to bounded linear from X to Y. That is, P is continuous. Then the graph is closed in X cross Y. Okay. This set I am talking is closed if T is continuous. Okay. That's a simple proof. Okay. So let Z belong to Z, G be a limit point. How do you show some set is closed? You show that every limit point is in that set. So since it is in G, so this Z, okay, this is sorry, it's a limit point of G. It is not in G. Okay. Since it's a limit point, this implies there exists a sequence, say Pn converging to Z as n tends to infinity, and Pn belong to G. That is what the thing is. What is that we want to show that? We want to show that Z is in G. What do you mean by Z is in G? There exists a Q, so Z will be equal to Q comma T, TQ. Okay? This is what we have to show. I'm saying to show that. I have not shown yet. So this Yn is, sorry, Qn, or I don't know what notation I have used. Okay. Pn, okay. Tn belong to G implies there exists, say, An in X such that An comma Tan belongs to G. That is by definition of the graph, by the definition. Okay. Now this An comma Tgn, say, converges to Z. Okay. This is part of the, this belongs to X cross Y. So call this Z as, say, some U and V. Okay. Now this An, T of An converging to this Z, Z is nothing but U comma V, implies and by implies, this is in product space. Okay. This implies that AN converges to U and TAN converges to V. AN converges to U implies TAN converges to TU because T is continuous. Okay. Now T of AN also converges to V. So the uniqueness of limit tells you, therefore TU equal to V. Okay? U is already, this AN is converging to U, therefore it is in X itself. Okay? So this point Z, this Z will be nothing but U comma TU. This means it belongs to the graph G. G, this point, this Z is a limit point of G, implies that G is in, Z is in G. Therefore, G is closed. Clear? Therefore, if T is a continuous map, then the graph is closed. What the closed graph theorem says is, if you have a map T from X to Y and the graph of T is closed in X cross Y, T continuous implies, sorry, the graph is closed implies that this is T is linear. Okay. Then T is continuous. So the graph is closed from, this is a Banach space. Okay. Then the T is a, so the graph of the function is closed, then the function it becomes itself will become continuous. That's the closed graph theorem. Now you can show that open mapping theorem implies closed graph theorem. This proof is very simple. Okay, so this is the proof which I am trying to give you. But if you see in many books, they first prove the closed graph theorem and then they show it's a open mapping theorem. This is also true. You can do it other way around also. Closed graph theorem also implies open mapping theorem. That also is true. Since we have done open mapping theorem now, so we will show this in the next class. I'll do it tomorrow. Okay, it will take some time. I'll give you some examples that open mapping theorem and closed graph theorem may not be true if X and Y are not complete. I have sent an assignment to you. In that it says on C00, I have given you a linear operator which is invertible. T is continuous, but T inverse is not continuous. You remember that example, no? Assignment problem. That you have C00 and you take a map, take an element x1, x2, xn. Then we defined a map Tx equal to, I hope I'm correct, x1, x2 by 2, etc. xn by xn. N. Dot, dot, dot. Then we showed T inverse exists, but not bounded.
Yes, sir, due to n will come from.
Yeah, right. This is an example which I sent you there. But T is continuous. T is continuous, it's on to, everything is there, but the T inverse is not continuous. This is because this C00 is not complete. So this preparatory example I have already given to you in assignment. Open mapping theorem is not true if you delete the what is called the Banach nature of the domain space. right? So that is a very quick way of doing it. So what I wish to tell you finally is that open mapping theorem is a too large a theorem. Nobody may ask you the proof. I will not ask you a proof of the whole open mapping theorem. But part of the open mapping theorem can be come in the question, right? That is the lemma. There are three parts, right? A, B, C. So I can tell you, assume A, prove B, or assume B, prove C. Something like that can be asked in the examination, because asking for the whole theorem doesn't make any sense. It is too big. Okay. Kush criteria. Kush Kataria. I want to tell you the whole theorem may not be asked, but part of the theorem may be asked. Okay. Last comment before I stop the class. I have sent all the notes, whatever I have taught till now, by PPT to you by email. Kindly download it and read it whenever
Yes,
you
sir,
want.
we got all
Yeah, if you
notes.
want something more, you please let me know. I will send it to you. All right. Bye bye. Have a good day. Enjoy.